Alright, so we're going to look at gravitational time dilation. So we've seen Interstellar, and in that we found that there was time, they call it time slippage, which is just time dilation due to being next to the black hole. Trying to figure out how to explain this. So I'm going to show a picture from my computer. That's what I'm going to show you. We're going to look at space-time and gravity, and I'm going to hold up this picture and we can see something. Okay. Just finding what I like. Here we go. Let's look at this one. Just going to get it up there. Ideally, if I edited videos better, I would just throw it in there. But we can have this one here. So each of the little square, the boxes there, they're not really square on this one. And then see how they dip down around Earth? Earth is creating like a well around it. Each of those little boxes gets stretched out as it goes down towards the Earth. So we're changing time. That's the boxes represent time and space. So not only is space being changed, but time is also changing too. And here's another one for something bigger. I think it's supposed to be the sun because I think there's Earth orbiting somewhere. But if it was a black hole, we would see those dots, or the squares, just keep stretching out as they go down. That's time being stretched out due to gravity. It's actually changing what space would look like if we could see it. And so time gets stretched out there too. You wouldn't notice time changing if you were falling into that black hole because you are also being stretched out. You are part of space. So you would physically get longer to match that time changing. You wouldn't notice though. Somebody on the outside would notice you go, right, as time changes, and then they would get old and die as you don't age, basically. So that's what they're looking for in there. That's what gravitational time dilation is, though, is we've warped space around you and time, because they're the same type thing. So we need an equation to reflect that for time dilation. So we end up with this. It looks similar to our velocity in time dilation 1, but it's going to be a little bit different. RC squared. You may remember we had before big G m over r squared. They've basically taken this equation and mixed it with that velocity one. But instead of velocities, we've got gravity and mass interacting there. We don't need that equation. I'm just showing you, like, how do we get this one? And that's really what it came from, and they've, due to humans, modified it around a bit. Yeah. So that's what we've got. Let's write our unit, or label all the variables here. So I'm going to just kind of make a list of what they are. So we have two times, right? We have t prime and t. I always double check because I always mess this up. This is outside our frame of reference. Reference. So this is our observer. So like if we are, let's relate it back to Interstellar. In the movie, 3 of them go down to, they call it Miller's Planet. It doesn't have an actual name. It's the one with the big waves. And they're down there for a couple hours. It'd be a couple hours, but they come back, and there's a guy that got left up in space. The guy outside in space experienced like 28 years. He aged 28 years. He's outside our frame of reference. Inside the frame of reference is the next one. This would people on the planet. So they experienced a couple hours, while the other guy experienced a long time because he was outside the frame of reference, and he was away from where gravity was affecting it, which is really how you're going to tell. It's really kind of like where you're looking from, and two, since we went to the planet and we followed their story for that couple hours, they get to be inside our frame. He got stuck outside. Alright, so our next one, we have big G coming back. And that was the universal gravitational constant. That was 6.67 times 10 to the negative 11th. And then there's some units, but the units are just for canceling stuff out, so I don't worry about them. As long as you remember your time and your mass and radius units, it shouldn't be an issue. So now M is mass of, I'm going to put planet, star, or the black hole, whatever you are near that's going to have a lot of mass. You have to use the planet or whatever it is because you don't have a lot of mass, right? You're like, 60 to 80 kilograms probably, somewhere in that range, and the planet is in the order of millions or billions of kilograms, and that's a small thing considering stars are even bigger and black holes are even bigger than that. I mean, one of our problems looks at the black hole at the center of our galaxy, and it's like 1,000,000 times, something like that, 4,000,000 times the mass of the sun. 400 million, I think. No, 4,000,000 times the mass of our sun. So your mass is pretty insignificant in comparison. So only worry about the mass of like the big object. Yours won't change anything really. Radius. That's the radius of our planet, star, or the black hole, whatever we are near. We measure our mass in kilograms, forgot to mention that, and then our radius is measured in meters. We need those units. Time is going to vary. We just need a unit of time. We can use seconds, we can use hours, years. Just know that whatever you put on, because we're gonna solve for one of these. You're either solving for inside or outside the frame of reference. If you put in years for outside the frame of reference, you're gonna get years here. All these other units cancel out. So really you don't need to worry about units here except for making sure they're in the correct units, kilograms and meters, and then time is gonna be our big unit one. Alright, I think I'm going to move the camera over a bit, and then we can work out a problem. Let's work out number one on the assignment. I'm going to have to move this for a second. I'm going to get a little shaky here. Okay. There we go. So now we got room. So I'm going to work out number one on the gravitational time dilation assignment. It says, how does 1 hour on Earth compared to the same time on Jupiter? So we're comparing Earth and Jupiter. So we're going to need the mass and the radius of Jupiter. We're going to assume we are standing on Jupiter and comparing it to Earth hours. Keep in mind, our watch would tick just normal for us. We wouldn't notice any change. It would be different though if we compared our watch, your watch on Jupiter after some time comparing it to Earth. It'd be slightly off. Okay. I'm going to start with rewriting my equation. I always like to start with that. And then we'll plug in from there. I'm going to leave some space so I can plug stuff in. Okay. I'm just going to write right in there and erase stuff so we have it and go from there. So we have 1 hour on Earth. We're assuming we are on Jupiter, so our frame of reference is going to be Jupiter time. We're going to solve for t. That's what we want. So my outside frame of reference is 1 hour on Earth. So 1 hour here. I'm going to need mass of Jupiter, which is on the assignment 1.91 times 10 to the 30, wait, that's not right, to the 27th kilograms. Yeah. And then I'm going to need the radius of Jupiter, which is also given to us. So we have 7.14 times 10 to the 14th c squared. I left c squared because it's a oh, I didn't put it up here. We'll put it, c is the speed of light. That's a universal constant, so we don't have to worry about that. That's 3 times 10 to the 8th meters per second. Hopefully that's got pretty small. Maybe I will put it here. So I'll put 3 times 10 to the 8th. That's meters per second, and that's going to be squared. Okay. Maybe I'll just rewrite it all, so it's a little more user-friendly. So we have 1 hour is equal to t over 1 minus 2. I'm going to plug in g, which is 6.67. Now say it and write it. Times 10 to the negative 11th. With some crazy units, I don't want to write them all. So we have 1.91 times 10 to the 27th. That's kilograms if we want that. Put the dots so we can see it's multiplied. 7.14 times 10 to the 14th. That was meters. That's going to be multiplied by the speed of light, so 3 times 10 to the 8th. That was meters per second. I didn't write those. And that's squared. Okay. Here's how I plug this into my calculator, so we following the same thing. I'm going to start here. Start, not stat. Start there. We can stat there later. Yes. So I'm going to take 2, I'm going to multiply it by the gravitational constant, 2 times 10 to the negative 2.2 times 6.67 to the negative 11th. And then I multiply that by the mass, so 9 or 1.91 times 10 to the 27th. I end up with, I'll write these as I simplify, 2.54794 times 10 to the 17th. So we're here. I still have to divide by this number. So what I'm going to do is I'm going to take this number, I'm going to divide it by the 7.14 times 10 to the 14th. I don't want to do all this. I don't want to show all this. Then I'm going to get some answer, and then I'm going to divide that answer, I'm going to draw another line here, by the speed of light squared. Okay, so I'm going to take this numerator, what it equals here, the 2.54, divide by the radius. So 7.14 times 10 to the 14th. I hit divide. So I get 356.85. And it keeps going. And I'm going to divide that by c squared, speed of light squared, so 3 to the 8th squared. Plug that in my calculator. I get 3.96, and it keeps going, times 10 to the negative 15th. Draw an arrow there. That's what I got. Simplifying this down. I'm going to get rid of this stuff here so we can write here. I'm going to rewrite what I've got so it's legible where I'm at now. So I still have 1 hour is equal to t over, I now have 1 minus 3.965 times 10 to the negative 15th. This is where I'm at. So I'm going to take 1, I'm going to subtract out my answer from this number. Uh-oh. It gave me 1. I don't like that. This time it gave me 1. I've done this before and I get a different number. What is going on? So my calculator is making an approximation. Before, I had gotten 0.999, oh, why am I writing my 9 so bad? So 0.9999999. I think there's one more 9. 6. That's what I should have gotten, something like that. And then I would square root that to get to point, how many 9s? There's 6 9s, I believe. 7 9s. I need one more. 8. That's what you should get. Basically it's 1. If you use a graphing calculator, you come up with 1. Right, then we can multiply that by 1 hour. So this is our hours on Jupiter. It's basically 1. Right, because we're talking a few seconds different, which we should expect, because in comparison to the mass and radius of Earth, Jupiter's not that much different. I mean, Jupiter's huge compared to Earth, but it's also less dense. So we shouldn't see as much gravitational distortion because it is less dense than Earth, because it's made out of gas. It does have big volume, and does have way more mass and more volume, but the density isn't there. So we shouldn't see much difference, and it's not a huge mass in comparison to like a black hole, which again is orders of magnitude bigger. So we expect it to be pretty close. Same with when we even compare the Earth. We expect it to be pretty darn close to an hour, because the Sun and Earth aren't even that much different in mass and density, which is going to make our difference compared to like a black hole. We need that black hole to make a bigger difference. Cool.